A very good evening everyone. Welcome to the video on RF oscillators. So let us first talk about the term oscillators. Now how do we define the term oscillators? It is any kind of a device that generates a waveform without requiring any input. And what is RF? It is radio frequency. So which means I need to generate waveforms in the radio frequency or microwave ranges which are very high. So to generate such high frequencies, that is where we talk about voltage controlled oscillators. We first try to generate oscillations, and by controlling or tuning the voltage values, we bring out oscillations which are in the RF and microwave ranges. So I once again repeat, we initially generate the oscillations by altering the characteristics of certain devices, and once oscillations have been produced, we tune or we adjust the voltage so that the frequency of oscillation lies in the RF or microwave range. Now, this represents the block diagram of the RF oscillator. We have three main blocks. One is the generator tuning block, then we have the NR device, then we have the terminating network. NR stands for negative resistance. Fine. We know what is resistance already. So resistance means we know that resistance, it opposes the flow of current. But now we talk about negative resistance. So which means it is the opposite of resistance. It is going to generate power for us. So normal resistance opposes the flow of energy, whereas negative resistance helps us to generate energy. So by using the negative resistance property of certain devices, we are going to see how oscillations can be generated. So this is the function of the NR device that is present here. Coming to the generator or tuning network, this is where oscillations are produced. This helps us to tune the oscillations to the required level that we want. And the terminating network is used for loading. So I hope that you remember what we studied about loading in the initial units. Loading is a process where we do to achieve a distortionless condition, which means I want the oscillations without any external noises. So to ensure proper oscillations, we have a terminating network which is a proper loaded one. Now this tau G, tau in, tau out and tau T, they are the reflection coefficients. Tau G is the reflection coefficient of the generator. Tau in is the reflection coefficient of this input of this device. Tau out is a reflection coefficient at the output of this device, and tau T is a reflection coefficient of this terminating network. Now what is negative resistance? So as per Ohm's law, we know that V is equal to I into R. So this is a direct proportionality and there is no phase difference. But in negative resistance, the voltage and current are 180 degree out of phase to each other. So 180 degree out of phase means it denotes inverse proportionality. If I increase one quantity, for example, if I increase voltage, the current will decrease. If I increase current, voltage will decrease. So due to this inverse proportionality, we cannot use this law. We don't use this law here where resistance prevails. We use the same law with an inverse proportionality that helps us to generate power. And we saw about this already in the previous slide. The tuning network, it determines what is the required oscillating frequency, and the terminating network, it provides the required loading for us. Coming to the condition of oscillation, we would have studied the reflection coefficient K in the previous units. So if reflection implies oscillation, if oscillation has to be 0, K must be 0. If oscillation or reflection must be present, K must be equal to 1. So if in case K is less than 1, it implies there are no or less oscillations, and we call that to be the unstable condition for an oscillator, because our main motive here is to generate oscillations, which means reflection has to be present. So therefore, if K is less than 1, we conclude the oscillator to be unstable in nature. Then when will that be called to be stable? I need the reflection coefficients to be a value equal to 1 both at the input as well as at the output. Only when the coefficients are 1, we can say that efficient oscillations are produced. So initially when they are not equal to 1, very less oscillations. So these are actually the noise components. These oscillations are due to the noises that are present. So the oscillations are produced due to noises, and as the required condition is achieved, we can see that a stable oscillation is produced in the given circuit. Now, coming to the concept of voltage controlled oscillators. So we saw how to generate oscillations. We are going to use the negative resistance property and we are going to generate the oscillations. Now what is going to control my oscillations is the next question. That is why we study about voltage controlled oscillators. So to control the oscillations, we are going to use a diode called as varactor diode. I hope you know the symbol of a PN junction diode. It is this. A varactor diode is similar to that, but it has two lines, where two lines means the variation in capacitance. The main concept of varactor is variation in capacitance. That is why the symbol is presented as such. And varactor means variable reactance. Fine. The term varactor stands for VAR is variable. This stands for reactance. So we are going to change the capacitance of this varactor diode. By changing the capacitance, we are going to change the frequency of the given oscillation. So change the input voltage. I'm going to change V. Changing V changes the capacitance of the varactor diode. Changing the capacitance changes the frequency of oscillation of the given signal. I hope you're clear with the flow. So first we'll change the bias voltage. Changing this voltage changes the capacitance value of the varactor diode, and by change of capacitance we are going to change the oscillating frequency. Now how to achieve this change in capacitance? So we all know, let this be our diode. So our diode contains two terminals. This is the positive terminal, this is the negative terminal, and this is the depletion region where both the positive, the holes and the electrons meet each other. Now we are going to connect this to a reverse bias. Only when this is given reverse bias, the capacitance of the varactor diode can vary. So we are going to produce a reverse bias. We are going to give a reverse bias to the varactor diode, and when this reverse bias voltage is changed, this region actually acts as a capacitance. This acts as an internal capacitance. The capacitance of this keeps on varying, which in turn is used to control the frequency of oscillation of the given waveform. So if you see here, I'm going to use varactor diode for frequency tuning purpose, and it is similar to a PN junction diode where we are going to use the voltage sensitive property, which means by changing the negative resistance voltage, we are going to change the capacitance of the varactor diode. And since capacitor is a function of frequency, or frequency is a function of capacitance, we are going to control the frequency of oscillation. Now these are the defining equations of varactor diode. So Cj stands for the junction capacitance that is created at this point. The capacitance that is created at this particular terminal, that is called as the junction capacitance. Cj naught is, even though we do not give an external reverse bias, without any external supply, there might be a small amount of capacitance at the junction. So this is the capacitance at the junction without any bias which is given to the circuit. VA stands for the applied voltage to the PN junction, and VBI stands for the built-in voltage. This is again a leakage voltage which is present inside your given PN junction. Now if you see here, this capacitance and the voltage components are inversely related to each other. So by changing the voltage, if I give a very high voltage, capacitance will be small. If I give a small voltage, capacitance will be high. So by varying the voltage value, we are going to try to vary the capacitance, which in turn controls the frequency of oscillation of the device. And S is one of the important parameters that determines the capacitance value. S is the doping profile of the varactor diode, and it is given by 1 by m plus 2. Now let us consider S to be half. So this will become Cj naught divided by root of 1 plus Va by Vbi. So this is the formula we get when we substitute the parameter S to be half. When S is equal to half, this is the characteristic of my PN junction. This is called as an abrupt junction because we have the hole concentration here, we have the electron concentration here, but when you take at this particular junction, I have to move from a maximum value just like that to 0 and then again to a total nu, which is an electron there. So here it is totally holes, we suddenly come to 0, we totally go to electrons. So since there is an abrupt transformation, we call this to be an abrupt region. Similarly, when we take S is equal to 2, here it is written as N, it is actually S. When we take S is equal to 2, it helps us form a hyper abrupt junction. Why it is called as hyper abrupt is because if you see this graph, it is either a maximum at the positive, maximum goes to maximum at the negative. Again here, maximum at the negative, maximum at the positive, it is like that. So if I have to transfer in between junctions, I have to automatically come from the maximum value to 0, again to maximum. Again maximum to 0, again to maximum. That is why these regions are called as hyper abrupt junctions. So by substituting various values of S in this particular formula, we can change the concentration of the N and P values, and when the concentration changes, based on that, the capacitance in this between region will get varied. That is why the doping profile is an important factor in the varactor diode. Now this is a formula for sensitivity. Sensitivity means how much the capacitance varies with respect to voltage. This actually inversely proportional, so it has to be C into 1 divided by V. Decrease in voltage, increase in capacitance, so it has to be an inverse relation. That is why we have dCj by Cj. Actually it will be 1 divided by dVr divided by Vr. This is the voltage of the varactor diode, right? When you reciprocate this term, we'll get it to be Vr dash by dVr dash. So it is actually the variation of capacitance dCj divided by with respect to capacitance into inverse of the voltage. When this is reciprocated, we get Vr dash by dVr dash. So this inverse relationship where the voltage and the capacitance are inversely related, this is called as sensitivity of the varactor diode. And this is an important 2 marks for us. They'll ask us to define what is sensitivity. We need to write this particular formula. And this diagram we saw already. It is the formation of abrupt junctions and non-abrupt junctions. Now why are those abrupt and non-abrupt junctions important? Now if you see here, we'll just see the two graphs with respect to those equations. This is a plot of equation 1. Equation 1 is this one. So as voltage increases, capacitance decreases. So if you see here, this is a reverse bias characteristics. Actually, we cannot operate the varactor diode in a forward bias because that will not give us the negative resistance property. We operate the varactor diode in a negative resistance region, or which is called as a reverse bias region. That is why we have the scale in a reverse value here. So we will make the voltage variation from here to here and observe the corresponding capacitance variation. Now when the voltage is increased to a certain level in the positive scale, we come to the built-in voltage. At the built-in voltage, the capacitance is at the peak. It is too high, but this is practically not reachable. This is due to some internal property that the capacitance reaches the maximum value. So this we can never achieve. So we always try to operate the capacitance in the negative or the reverse bias region. And looking at this diagram, this gives a plot of capacitance versus the voltage and with respect to the various hyperabrupt junctions. So if you see here when S is equal to 1 by 3, the variation is a bit gradual. It is not too high or too low. At abrupt junction again, it is somewhat a gradual decrease. But for hyperabrupt junctions, we are able to achieve very high values of capacitances. So we will try to design the doping profile in such a way that we are able to achieve a hyperabrupt junction, and in turn we get a very large capacitance variation. When we achieve a very large capacitive variation, a equivalent large variation of frequency of oscillation can be achieved. So thus to conclude, the flow is like this. I vary the reverse bias voltage. Due to this, the capacitance of the varactor diode changes. Due to variation in capacitance, the oscillation frequency of my RF or microwave range changes. So since varactors are used for tuning the frequencies, the varactor tuned oscillators are hence called as the voltage controlled oscillators. Thank you.